All right, so in this video, we're going to be looking at vector fields and finding potential functions, either creating a vector field from a potential function or from a vector field finding the potential function, if it exists, that created it. So the first thing that we're going to look at is plotting vector fields. And if we have a vector field, and we'll start with a nice simple one, minus y I plus xj, then at each point in the plane, there is going to be a vector that is pointing in a particular direction. And so in order to plot the field, we have to plot these vectors. Now, typically, the way that these get plotted is you calculate the vector at a whole bunch of points. Typically, then you rescale the vectors for the graph. You don't plot them necessarily at the value that they come out as, because they may overlap with each other on the graph. So typically, when you're creating them, you'll rescale them by a particular value so that you can make sure that you can plot them and they're not going to run into each other on your graph. I'm going to use rescaling by 1/3, for instance, because that will accommodate all of my vectors. It'll keep them less than a unit length. And so they won't run into other points that are separated from them by 1 unit. But if you have an example where the vectors are longer, then you can rescale them by other amounts. So let's look at calculating our vectors. So again, at each point in space, we're going to have to calculate a vector, calculate the magnitude, and then rescale them in order to know how long the vectors need to be plotted. Now, typically, if you're doing this by hand, then you may just sort of eyeball them to make sure they're of appropriate length. But when you're certainly setting up a program to do this automatically, then you would want to rescale them consistently. And so that's the sort of thing that I have in mind here. So we're going to start with the origin. If I plug this y value into my negative yi component and this x value into my xj component, I get 0, 0. And so the magnitude is 0. There's no vector there. You can just put a dot, basically. At the point 1, 0 on the x-axis, I get the vector 0, 1. The magnitude is 1. And so the rescaled length is 1/3. Here, I'm going to plot the point 0, 1, which is on the positive y-axis. I get the vector -1, 0. The magnitude of that is 1. Again, just this is the modulus of the vector, the length of the vector. And then again, I rescale that. And then I continue. This is my negative x-axis, my positive y, or my negative y-axis. I get my vectors. I rescale them. And then I start spiraling outward away from the origin to look at, let's say, my 1, 1 points. Again, this is the negative y, this is positive x, just plugging them into my vector formula. The magnitude has gotten larger as I go away from the origin. And if I rescale that by 3, I get about 0.47. This is, again, these are basically the coordinates of my square box around 1, -1, -1, 1, negative, negative, -1, -1. Again, plugging them into my negative yi plus xj formula, I get all of these vectors are the same length. And then I continue, again, just spiraling outward to 0, -2, 0, 0, 2, 0, -2. I get these vectors. They're all length 2. Rescale them to be 2/3, about 0.67. And then again, I continue to move outward from the origin to 1, -2, 1, 2, -1, -2, 1, 1, 2, 1, -2. Again, I'm just trying to fill in that area around the origin. And then finally, my 2 by 2 box corners, 2, 2, -2, 2, 2, -2, -2, -2. I get my magnitude And now again, this is where my graph is stopping. And so I'm still just about length 1, which is why I chose 3 in the first place. And now if we use technology then to quickly plot all of our points, we get a graph that looks like this. So it is, in this case, spiraling around the origin. Our 0 vector in the middle is not going anywhere. But then we have, when we're over here, we're plotting directly across the x-axis, but here we're plotting downward, here we're plotting sideways, and so forth. And so we get this spiraling effect as we plot points in the plane. Notice that as we go away from the origin, the vectors are still pointing in the spiraling direction, but they're getting larger and larger as we go away from the origin. And this is why we scale them, because we don't want them to run into each other. If they were all sort of standard scale, especially around the center, they would all kind of start overlapping and it would become very difficult to read the graph. Now we can look at a 3-dimensional graph, and I used the Java applet to plot this because plotting even standard just single vectors in 3D is kind of a hassle. I deliberately picked this one because it's a little bit more chaotic looking. Your vector fields can seem very well behaved, or they can be much crazier looking. But we would, again, if we were trying to plot this, we would be trying to plot individual vectors. We'd pick points in space. We'd plug them into our equation up here to get our 3-dimensional vector. And then we would attempt to manually plot them on a 3-dimensional grid. Now, the perspective can create more of a problem, which is where technology can come in really handy. Generally, professors will have students plot 2-dimensional vector fields if they do that at all. 3-dimensional ones generally we reserve those for technology. Now, when I want to start with the potential function and I want to create a vector field from that, I'm going to create a conservative vector field from this potential function. And the way that we do that is we calculate the gradient of the function. So the gradient is basically just the vector of partial derivatives for this function. So if I take the derivative for x, then in the I component, I'm going to get 2 over x. And if I take the derivative for y in the j component, I'm going to get 1 over y. And that's all you have to do. That will give you a conservative vector field. Now, if I want to go in the reverse direction, say I have a vector field like this, and I want to find the potential function for that field. Now, there's no particular guarantee that it exists, but it will exist if the field is conservative. There are tests that we can do to determine if it is in fact conservative, but we can also just attempt to find the potential function. And if we are unable to find one function that can produce both of these outcomes, then we know that the field is not conservative. In this particular case, the field is in fact conservative. So here, what we do is we take our I component, whatever it is, and we integrate with respect to x. And so what we get in this case is 2 x terms. And then what we're not able to reconstruct are any terms that contain only y. In this case, because this m function, if it is a conservative vector field, this will be the derivative of x with respect to our potential function. And so any terms that had only y in them will have disappeared when we took the derivative. Similarly, the j component will be the derivative with respect to y if the potential function exists. And so any components that had only x in them will not survive when you take the derivative for y. And so we're going to take our n component and we're going to integrate with respect to y. At least here we'll be able to reconstruct our y components. Now, if I have any terms that appear in both of these expressions, then that would appear at one time in my potential function. And then I would look to each of these separate pieces in order to get my x only components and my y only components. In this case, I don't have any xy terms. I just have x only terms and y only terms. And so my potential function is going to just be the collection of those 4 terms plus some constant, which I still can't recover. Now, in a more complicated example, this one in 3 dimensions, we're still basically going to do the same thing. If the field is conservative, then if I integrate this I component with respect to x, this is supposed to be the derivative with respect to x if it's conservative. So integrating it with respect to x, hopefully I'll be able to recover at least the terms that contain x. Same thing for integrating the j component. N is supposed to be, if the field is conservative, the derivative of the original potential function with respect to y. So I integrate for y and again, hope that I can recover my components that have y in them. And then same thing for p. This is now the derivative with respect to z. And so I'll integrate with respect to z to again try to recover those terms that contain z in them. The terms that I won't be able to reconstruct in each of these will terms that contain only y and z in my x antiderivative, terms that contain only x and z in my y antiderivative, and then terms that contain only x and y in my z antiderivative. Now, once I've actually done the antiderivative here, I look at my function. So any term that has all 3 variables in it should appear in all 3 of my antiderivatives. So I see xyz, xyz, xyz. They're in all of them, and that goes into my potential function. Now, these have to match each other or there's no potential function. But here they all match, and that one term goes only one time into my potential function. I'm not adding these terms together. I'm identifying that there is a common xyz term in each of these functions, and so it goes into my potential function proper. Now, if I have any terms that contain 2 variables, then they need to appear in 2 of the components that have those same variables. So here I have an xy term and I have another xy term. So they have to appear in both the x antiderivative and the y antiderivative. And then again, I don't add them. I take one copy of them and I stick it into my potential function. Same thing for my 2yz term. If it in the potential function, it has to appear in both y and z antiderivatives, and it does. And so this 2yz can go into my potential function. Again, not the sum of it, just one copy of it. And then any terms that contain only x, only y, or only z will only appear in one of these antiderivatives. And so then again, I will take those terms and I will stick them into my potential function. So I'm going to include the negative x squared, the positive 2y squared, and the negative z cubed. And then when I put all of those together, then I'm going to end up with my final potential function, my 3 components, my 2 variable components, my 1 variable component, and then the constant that I can't recover. Now, in 2 dimensions, you can actually determine if there is a potential function or not by checking to see if the derivative of your I component with respect to y is equal to the n component with respect to x. This is basically if m is the derivative for x and you take the derivative for y, you get the mixed partial. And if n is the derivative for y and you take the derivative for x, you get the other mixed partial, and they have to be equal. And so if these are not equal to each other, then there is no potential function. There's not one function that these are the mixed partial derivatives for. If you have 3 dimensions, you have to do the curl, and that is a much more elaborate calculation, which is discussed in another video.